Hello again. We're going to try to do some slideshows that are a little shorter, and hopefully that will make it a little more tolerable. And also, I'm hoping that we don't get this freezing problem. So let's begin by recalling the video I asked you to watch before the break about the electromagnetic spectrum, about electromagnetic energy. Electromagnetic energy, that which is, as we should remember, produced in the sun by the process of fusion. The fusion of hydrogen elements, the most basic element, one proton, one electron, fusing together to form the second element in the periodic table, helium. And the magic of that reaction is that the total mass of the hydrogen that is fused is greater than that of the mass of the helium created. And that reality was defined mathematically by Einstein in his famous equation E equals mc squared, that there is an equality between energy and mass of a material that relates to the speed of light, that which electromagnetic energy travels at. And what Einstein was able to intuit, and that eventually was experimentally demonstrated, was that the loss of mass from that heavier hydrogen that fuses to that new element helium that is formed, that loss of mass is transformed into energy, and that energy is electromagnetic energy, which then travels through space. And then we want to just look today basically at our eyes in relation to electromagnetic energy. But down below here we see what is called the electromagnetic spectrum, with the longest wavelengths. These are waves of electromagnetic energy. The longest waves, radio, then our microwaves, then our infrared waves, and then this small area of the electromagnetic spectrum that contains visible light in the rainbow of colors that we can see. Then once we move beyond violet, ultraviolet, we go to invisible, higher energy waves that can be damaging to life. Ultraviolet, X-rays, and gamma. And again, we want to then relate the electromagnetic spectrum and energy to first our vision, then the discovery of lenses that could focus electromagnetic energy, and finally telescopes, which opened up the understanding of the universe that we have today. Electromagnetic radiation is generated in the sun by a process called fusion. Fusion occurs when the atoms of hydrogen are fused to make one new atom of helium, releasing electromagnetic radiation. Again, I just described that. Hydrogen is fused. That initial hydrogen has a particular mass. The new helium has less mass. That mass that is missing or disappears has been transformed into energy. From radio waves to gamma waves, the sun is said to produce a continuous spectrum of EMR. Most of the EMR leaving the surface of the sun is visible light. Gamma rays, X-rays, they get trapped in the sun. And other forms of radiation that might reach the Earth are trapped either in the atmosphere, by ozone, or the upper atmosphere. All electromagnetic radiation, EMR, the last point here, travels from the sun through the vacuum of space in waves at the speed of light, 300 kilometers per second. This is a wave. Now you might want to go back to this and refer to it in the future, because you're going to be asked to draw or create a wave like this. So we see that we have a line of reference. If there was no energy in a system, if no electromagnetic energy was passing through some point in space and then being registered at a second point of space, a start and a finish, there was no energy, there would be a flat line. But once energy is put into the system, the electromagnetic energy will travel in waves. The waves will move away from the line of reference, the line of point of rest, and create a crest. That distance up is the amplitude from the reference line, from the point of rest, to its highest point. Then down to the trough. The same distance, in many cases, from the reference line down. Then back up through the point of rest to the crest and back to the trough. Amplitude, and then our very important measurement of electromagnetic energy, the wavelength. What is the distance from the crest of one wave to the next wave? That is your wavelength. Here comes your solar energy distribution. How much of each type of energy is leaving the sun and approaching the earth? Smallest amount is in the ultraviolet range. Visible has the most intensity, and then our infrared from near to far, right? So there's a range. We have to remember this. There's a range within each particular form of electromagnetic energy. There is a range from, say, near infrared, which means near the visible, to mid-range to longest range. And then we have our different types of ultraviolet based on wavelength. The ones closest to violet and visible to the ones furthest and getting closest to X-rays. This would be another way to look at what arrives from the sun. And if we look at this, we see that if there are any gamma or X-rays that do leave the sun, most of them are trapped within the sun. They might make it into the mesosphere, but then are absorbed. Ultraviolet is mostly absorbed in the stratosphere by ozone, but some does reach the earth. That's what this section is here. All the visible light passes through the atmosphere and makes it to the surface. Infrared in some forms makes it to the surface, and in other waves doesn't. Microwaves a little bit, but the one that does most of all besides visible are radio waves, which is one of the reasons that humans invented radio telescopes. Radio telescopes are able to detect radio waves from outer space. Again, just another picture of your electromagnetic spectrum. Here is your visible light and color. And here you see the different types of electromagnetic energy that might reach the surface of the earth. And this is something that I've asked you about in an assignment. What reaches the surface of the earth? And if it doesn't, why not? The electromagnetic spectrum, as you need to understand it in terms of the Regents exam, is no more than this diagram found on page 14, the one on the bottom here. You just need to know that there are decreasing wavelengths, gamma rays, then going up to X-rays, then ultraviolet, then our visible light broken up into the famous violet, blue, green, yellow, orange, and red. Some people call the blue indigo. And then your infrared in a range. Some of the infrared corresponds to similar wavelengths of microwave, which you also see here, that X-rays can be found crossing over into the range of gamma and ultraviolet, and then radio waves, the longest waves of all. Up here, you see a comparison of, you can see some things that the electromagnetic waves can do for us. Radios, heating food, generating heat, allowing us to see. Ultraviolet has uses X-rays and gamma rays, which are very dangerous. Here is your human eye. I think it's important to just spend a little bit of time in this section on the eye, because the eye is really the key. We have other senses. There are people who can't see, but for those humans, the majority of whom that do, vision has been what has opened up an understanding of our universe. it might have been very difficult to come to that without our ability to see the eye that we have and its ability to transform electromagnetic energy in the visible range into images that we can then describe. And what we see here are the basic parts of an eye, where we have a film of liquid tears that cover the cornea, protecting the eye. Then we get into the iris, which has the ability to protect, again, the lens, and is able to expand and contract with the pupil, allowing more or less light to hit the lens. The lens, which then focuses visible light back on the retina. The retina, then, which consists of millions and millions of rods and cones, which are sensitive to color and or simple white light, black and white. So again, the image that you see is right side up, but is projected onto your retina upside down. This is a very common feature of lenses, where lenses take light through, and then that light is directed to the back, but the image is upside down. So how does the image become right side up? Well, the brain writes the image in the occipital lobe, the back of your brain. Light strikes the retina and stimulates rods and cones. Your rods and cones can be found beneath the retinal surface, and there are millions of them. The rods are sensitive to black and white, and it takes very little light to stimulate them. So that's why you can see as light is dimmed or towards the dark, because your rods are still able to pick up wavelengths of visible light. But your rods are more concentrated in your peripheral vision. So in fact, as you lose more and more light, you're getting more, you have your peripheral vision, it doesn't get better as such, it's just more sensitive than straight ahead, because your rods tend to be packed in this side of your retina, on the sides of your retina. Cones are sensitive, interestingly enough, only to 3 colors: red, blue, and green. And they take a greater amount of light to stimulate, which is why as light dims, you see less and less color. Each of the 3 cone colors is sensitive in a range of wavelengths that, when they mix, the full spectrum of colors can be created in your brain. So you can see that blue shares wavelengths with green and with red, and that green and red share wavelengths, and it's this mixing that gives us this range of colors that we see below, from violet to blue to cyan to green to yellow to red. So simply by mixing 3 colors, we can actually get all these colors of the rainbow. And then you can see the dots here represent what your rods can pick up, a much narrower range. And it's where the 3 blend, which is why to your eye it looks like white light. What happens once the retinal proteins, which is what these cones and rods are, what happens when they're stimulated by light? Well, they then send a signal, the right eye to the left occipital lobe and the left eye to the right occipital lobe, where the 2 images are combined into one that you see at this moment. And it is this beautiful system that allows us, and has allowed us for now thousands of years as Homo sapiens, to see the night sky, the sun in the sky, and in this image, what you might recognize as a waxing crescent moon with the planet Venus and the planet Mercury. And just to go to an image of our solar system that is quite remarkable. We see here Jupiter, Saturn, Mars, Venus, and Mercury all lined up. This is I think in 2002 it says here. They were all in the night sky together. And so this person got a beautiful picture. And of course, these are on the plane of the ecliptic. And it is our ability to see this that has led us to our insights about the universe around us today. With our eyes, we've been able to see and chart the solar system, creating a working model we call the universe. Humans also gained a limited understanding of the scale of the night sky they were observing.